A landmark study of the survivors of the atomic bombings of Japan was just published. The study presents the strongest evidence to date that cancer risk not only exists at low doses of radiation, but may be even greater per unit of dose than at higher doses. The study also demonstrates that ionizing radiation is associated with non-cancer diseases involving circulatory, respiratory, and digestive systems. In this video, we'll review this new study, examine linearity and nonlinearity in the dose response, and address some common misconceptions about the atomic bomb survivor cohort. In 1947, after the atomic bombings of Hiroshima and Nagasaki, the United States National Academy of Sciences founded the Atomic Bomb Casualty Commission to study the health effects of radiation on the survivors of the atomic bombings of Japan. In 1975, the commission changed its name to the Radiation Effects Research Foundation in cooperative association with the Japanese government. To date, the Foundation has published 14 studies on the health status of the atomic bomb survivors. As the Foundation's website shows, their research reveals a steady increase in radiation-related cancer mortality over the decades since the bombings, and that there appears to be no harmless dose of radiation, as depicted here in this cancer risk versus radiation dose graph, which best fits the linear no-threshold or LNT model. The Foundation's new 2012 study reports that the still evolving data from the atomic bomb survivor cohort continues to affirm the linear relation between harm and dose, and that there is no threshold below which radiation doses are harmless. Here then is the most current dose-response graph for the atomic bomb survivor cohort, covering the period from 1950 to 2003. The graph shows the relation between doses of radiation, scaled along the x-axis at the bottom, and increased cancer risk, scaled along the y-axis on the right. The red line highlights the slope for the linear model, wherein cancer risk increases exactly as radiation dose increases. While the linear model is the best fit over the entire dose range, it's not a perfect fit over smaller ranges. The authors report a trend of upward curving risk for doses from 0 to 2 grays, or sieverts, that has recently reached significance. They also report higher risk per unit of dose at the low end, displayed here in Figure 5, which shows the excess relative risk per sievert at specific doses. Notice that the lowest data point is at 20 millisieverts, the same level Japanese authorities set as the safety limit for the Fukushima prefecture. Obviously, this level should not be considered harmless. While the authors note that this non-linearity in the data is without causal explanation, a minimal interpretation is that lower doses of radiation are not harmless. Another important finding from the cohort is an increasing relation between radiation and non-cancer diseases, such as those involving circulatory, respiratory, and digestive systems. In Figure 6, the authors present these graphs that show how the dose-response curves for both solid cancer and non-cancer diseases have shifted over the course of the study. The dashed lines show the dose-response curves between 1950 and 1965, while the solid lines show the dose-response curves from 1966 to 2003. For both all solid cancer and non-cancer diseases, linearity has emerged as the dominant overall dose-response characteristic. It is curious to note that between 1950 and 1965, non-cancer diseases showed a notable hormesis-like dip at the low end, meaning the lower dose portion of the survivor cohort experienced fewer non-cancerous diseases than expected over that 15-year time frame. This result is consistent with the theory known as radiation hormesis. However, over the subsequent 3 decades, that hint of hormesis evaporated into the grim reality of systematic linear harm. Exploring nonlinearity in the dose response further, let's consider a study by the Foundation in 2000 that included this moving average dose-response curve over the truncated dose range from 0 to 500 millisieverts. And here's the dose-response plot from the Foundation's current 2012 report. We can see that the slope of the linear trend has dropped. This is primarily due to an adjustment of the estimated dose the survivors received, which was imposed in 2003. And here is a 3-dose moving average of the new dose-response graph zoomed in on the lower end of the whole dose scale. Notice that even as the data points have changed their relative positions as the cohort ages, the 2 curves over this low-end range have maintained a similar 2-peak, 2-dip shape. Advocates of the hormesis theory that low-dose radiation is beneficial might be quick to point out the single data point around 110 millisieverts that falls below 0 risk. Could this be a sign of a beneficial dose? In 2000, the Foundation published another report with separate dose-response graphs for Hiroshima and Nagasaki. Notice that in the Nagasaki-only cohort, there's a dip below 0 risk around 50 millisieverts. However, in the Hiroshima cohort, there was conversely a peak around 50 millisieverts. And when both cohorts are combined into one, Nagasaki's below 0 dip disappears. Let's observe how cohort size corresponds with dose-response linearity. Here we see Nagasaki's graph, which is remarkably non-linear. If this was all the data we had, we might assume some low doses may reduce cancer risk. We might also infer that after 750 millisieverts, risk no longer increases. However, consulting the Hiroshima cohort, which was over twice as large, finds no dose below 0 risk, and risk continues to rise upwards after 750 millisieverts. And overall, the whole curve is far more linear. And now let's step up to the highest level of data. The combined cohorts of both cities, 3 times larger than the Nagasaki cohort. And here we see the highest degree of linearity in the dose response. In these 3 steps, linearity consistently increases as cohort size increases. This correlation between linearity and statistical power is a good indication that the radiation dose response actually is linear overall. However, notice that just as seen in the current 2012 study, this study from 2000 also showed a nonlinear peak at the lowest dose end. In fact, a low-end peak was seen in each city. This temporal persistence and statistical preservation over cohort sizes is an indication that there may be an adverse nonlinear dose response at the low end. Furthermore, the fact that radiation-induced genetic damage has been found to be higher at the lowest doses further supports the likelihood that low doses are more harmful per unit of dose. However, as the authors of the recent study note, the meaning of this nonlinearity is unknown. Yet whether it reflects confounding influences or intrinsic properties of radiobiology, this nonlinearity obviously fails to support claims that low-dose radiation is harmless, because this nonlinearity occurs almost always above zero risk. The clear signal of low-dose risk in the atomic bomb survivor cohort that we've observed here undergirds radiation protection standards and risk modeling worldwide. Nevertheless, some experts disagree with the consensus and argue that the atomic bomb survivor cohort provides no evidence that doses below 100 millisieverts are harmful, because the data in that range are not statistically significant. For example, since the Fukushima disaster, Professors Yamashita and Allison have invoked this argument in their advocacy of allowing greater public exposure to radiation.
You need a large population of people who have been highly irradiated and another lot of people who haven't been irradiated to compare them with. And the most important set of data of this kind are from the survivors of Hiroshima and Nagasaki, where those who received doses of less than 100 millisieverts, the extra risk is consistent with zero, even in this extraordinarily large set of data. So it is perfectly respectable and sensible to consider that below 100 millisieverts, that's a single acute dose, there is no radiation risk.
Let's examine the data they cite to support their argument. Here are the previously published solid cancer deaths in the atomic bomb survivor cohort, which Professor Allison used in his talk. The data table stratifies cancer deaths into dose ranges. The two strata below 100 millisieverts are highlighted in green. And here are those data plotted. The allegedly safe dose range below 100 millisieverts is highlighted in green. Now, statistical significance is an arbitrarily chosen p-value, which under various circumstances may range from 0.1 to 0.01. For epidemiological research like this, 0.05 is usually chosen. So in that case, this value for the doses from 5 to 100 millisieverts is not statistically significant, as Yamashita and Allison observe. However, there are good reasons, too numerous to cover here, why this hasn't swayed the scientific consensus on radiation risk. For example, let's consider what this p-value means. Two hypotheses are under consideration. The null hypothesis, or H0, proposes that the risk value, or ERR, is equal to or below 0. In other words, hypothesis H0 proposes that doses from 5 to 100 millisieverts are harmless. So the p-value means that the probability that hypothesis H0 is true is 10%. Therefore, the p-value also means that the alternative hypothesis, H1, which proposes that risk is greater than 0, has a 90% probability of being true. In other words, the probability that doses from 5 to 100 millisieverts are harmful is 90%. If the chance of rain was 90%, would you take an umbrella? If you had a 10-round revolver with 9 bullets loaded, would you take aim at an innocent and pull the trigger? Just as the rational person takes her umbrella, ethical radiation policy experts don't play Russian roulette with public safety. 2 of the atomic bomb survivor scientists, with the Radiation Effects Research Foundation, expressed the consensus view in addressing the question of doses below 100 millisieverts, saying, quote, "In the presence of available data, it is neither sound statistical interpretation nor prudent risk evaluation to take the view that the risk should be considered as 0 in some low-dose range due to lack of statistical significance when restricting attention to that range."